Okay, so here we have our graphs. We have the motion graph of x of t, v of t, and a of t. As t is in time, probably seconds, most likely seconds. So x as in a unit of seconds, velocity in a unit of seconds, and a as a unit of seconds. A as an acceleration. So first we have to start out with x of t. X of t, we look at the motion graph, and if you think of a ball, so a ball, you throw it up into the air, and it comes back down after let's just say 6 seconds. So this is 6 seconds. T is on the x-axis. So after 6 seconds, after 6 seconds, it hits the ground again. Imagine you're throwing it up from the ground. It comes up, reaches its peak, and then comes back down after 6 seconds. Well, so what's the velocity doing at that time? We have to understand that velocity is a vector. It's a vector. It's not a scalar. The difference between a scalar and a vector, so a scalar is just magnitude. And it does not include direction. A vector is magnitude plus the direction as well. And what I mean by that is that a scalar is only going to measure how fast the thing is going. It's not going to measure where it is according to your, I don't know what to call it, your 0 point, your v naught, or your x naught. So the scalar only measures the magnitude. A scalar is like speed. Like if you think of the word speed, you're not actually knowing where you're going. Where velocity, it's different. Velocity is the speed of an object plus the direction it's going. So that's why here velocity, if this is 0, we have a negative number. We get into these negatives. That means that the velocity is going down. It is going opposite. You want to be able to know that this is opposite of positive. And if we establish that positive is going up, this must be coming down. So what this means is, at the start of his throw, I throw a ball up, it travels across this loop, or this arch. It travels along this arch until it reaches its peak and it falls back down. At the peak, the velocity is 0, which is this point right here. So when this is 0, when it hits 0 right here, that's when this x is right there. It's at its peak. It's not going anywhere, it's just sitting at the top. Now it's starting to travel downwards. The ball is coming back down to earth, therefore the velocity is negative. It's going the same speed, but because it's a vector, velocity is a vector, the direction makes this velocity negative, which means the graph is going to keep on going downwards. So the acceleration here, I forgot to draw the line, but is down here. The acceleration is going to be gravity. Now gravity we know is 9.8. However, it's negative 9.8, right? We can use 9.8 or 9.81, or you could even use 10. On the AP test, you're allowed to use 10, I'm pretty sure. But it's negative 9.8. So this is our acceleration for an object in free fall. So we see that there's an arch. It hits the peak, right? At the peak, the velocity is 0. The acceleration, however, is still the same. It stays the same. Gravity is always pushing on it, but the acceleration makes this velocity 0. And at that point, it starts to head back down to earth. So we have to know that velocity is the change, which changes, we use delta, change of x over the change of time. The change in position over the change in time is velocity. Now, acceleration is the change in velocity over the change in time. So in calculus, you're going to learn derivatives and you will be able to relate these two graphs together eventually. You'll be able to figure this out. But just know that velocity is the change in x over the change in time, where acceleration is the change in velocity over the change in time. Now, acceleration, an object in free fall is always negative 9.8. Now we look at these equations I have written up here. These are fundamental equations of kinematics. The first one is the velocity at some position x is equal to the velocity when you start. This is x naught, right? So it's the starting position, the velocity at the starting position, plus the acceleration times the time it takes. This next one is the position is equal to the original position plus the velocity, the original velocity times the time, plus 1/2 the acceleration times the time squared. You want to use these equations when you know, most likely you'll know either an x and a velocity, and you want to solve for the ax or solve for the acceleration, or you know the velocity and the acceleration, and the starting position is 0, and so then you can solve for this x, and it's the same for all of these equations. You want to figure out which one works best for your for the equation at hand. So we'll get back to that. We'll try a few sample problems. Next, we're going to talk about displacement and distance. So, for instance, I draw this line. It's nice and squiggly, but it's on the same like axis, right? It's on the same line right here. Well, the displacement is just this line here. It is the shortest distance from one point to another point. This is the displacement right here. That's the displacement, this line. The distance is the total traveled, the total position traveled. It is this whole line. Those are the differences. The displacement and distance are completely different from one another.